Good afternoon. I'd like to start by, on this day of anniversaries, pointing out my anniversary. This is about 30 years, actually, since I was last here at this observatory. I used to work as a research assistant for the ANU, and I observed with the older ANU telescopes here in the 1970s. And then I became a graduate student at ANU, and I did my PhD there, that's in Stromlo in Canberra, and was fortunate, very privileged, to again use telescopes here and at Mount Stromlo before you guys decided to set fire to both of those observatories. But since then, I've left Australia. I've been back to Australia for many visits, but I've never actually been back to the observatory here. And I've worked at many different places. I've been privileged to work at many different observatories around the world. And most lately, for the last 7 years, I've been working on this project, which I will now describe as best I can. So, we are Las Cumbres Observatory Global Telescope. So we have telescopes here in Australia. We have a 2-meter telescope that's been here for 10 years. It's actually our 10-year anniversary for this telescope. And we have 2 1-meter telescopes here, which are over there at the site, which is here at the Siding Spring Observatory. In addition to that, we have another 2-meter telescope in Hawaii, and then more recently we have designed and built in-house these 1-meter telescopes. One is in Texas, another one is actually in Santa Barbara, which is our headquarters there. We have 3 of them in Chile, we have 3 in South Africa at the Sutherland Observatory, SAAO, and we are going to put 2 smaller telescopes here in the Canary Islands, Tenerife. And I've been to China a couple of years ago, and we've just recently had another team there. We're trying to negotiate a site in China. And the whole point of this is, as the Earth rotates, roughly half of these sites are in the dark. And therefore, we can monitor time variable observations, time variable sources, from somewhere on the Earth. So try to think of this not as a collection of telescopes, but as a single operating network, one entity, and we operate it with common software for all of these telescopes. All of these, the 2 meters had older software 10 years ago. They are all now operating on the same system, and all 11 of these telescopes have been operating on the same system since April of this year. And as we have a complete coverage in the south, so we can more or less cover 24 hours a day, and we're obviously trying to fill in this northern ring. And we keep them sort of separated. This is effectively time as the Earth goes around, and therefore we can bounce backwards and forwards certainly for equatorial objects that are accessible in this range from both north and south hemispheres. So this is us. This is the Las Cumbres Observatory Global Telescope. And okay, the top has gone off, but it doesn't really matter what the title is. We are a private, non-profit organization based in Goleta, which is near Santa Barbara in California. So all of our funding actually came from a single person whose name is Wayne Rosing. And he worked with Apple. He was heavily involved in the design of the Lisa computer, which was the first comprehensive science-capable computer way back when. He was involved with Sun, where he was heavily involved in the definition and build of the Java operating language, and that's what we use for our operating system. And more lately, he was involved with Google, where he was the chief engineer for building their server farms around the world so that the Google searches could work. And then he retired, and he decided, since he's a very keen astronomer, he decided to use his knowledge of technology, the internet, and etc., to build a global network using all of his knowledge and other people that he hired to actually get things done. So we started our operations, full operations, in May 2014, that's this year, but some of the telescopes have been operating for much longer than that. It's designed to provide unique capabilities for time domain. That's our niche. We are not building the world's largest telescope, although we are, in fact, a 12,000 kilometer telescope with a very small field aperture. And we do these kinds of, not exhaustively, but we do supernovae, we do microlensing, we do near-Earth objects, moving objects against the star backgrounds. We do variable stars, astroseismology, that's the pulsation of stars. And we do all of this. Anything that's time variable we consider to be our niche. And we don't usually discover these sources. We get the discoveries from other people, but we monitor it as often and as best necessary. We are also concerned to develop an effective, scalable, we're trying to expand, and sustainable. So we're trying to build a network which is not too expensive and can be sustained operationally. You know, or you probably know, that many telescopes then get threatened with budget cuts, particularly when we build newer and more expensive facilities. We don't want to get into that mode. We want to keep this thing going at a level which people, including our financial partners, can afford. So the science drivers are transient objects, so supernovae, gamma ray bursters, tidal disruption flares are all stellar objects, stellar microlensing, I'll explain more about this, microlensing exoplanets, transiting exoplanets, that's where the planet goes around in front of the star and there's a little dip in the light curve. What's called reverberation mapping, I'm not going to say much more about that, but when a source in the middle of a galaxy is exploding and blowing jets of material around, it starts interacting with the surrounding materials, and that time variability can take days or weeks or sometimes months. By simply measuring that time, you can work out how big that zone is that those activities are taking place in. And of course, we can also measure classical novae, other types of normal variable stars. We are involved in solar system moving objects, that's near-Earth objects, including asteroids and comets, and and trans-Neptunian objects, which are things like Pluto, way out beyond Neptune, and space junk. So you know that there's a big problem. Thousands of bits of things are spinning around in the near-Earth orbit, which have all been launched into orbit, and they have a possibility of colliding with the International Space Station or with another satellite and knocking that satellite out, or possibly killing people. So these are all things that attempt to be mapped and known about, and we do those. So what can I zoom this down a little bit? Because I'm losing the bottom part. Well, I'll just tell you what this here, this is brightness of supernovae. So this is all about supernovae. And a factor of 42 to 41, that's a factor of 10 in luminosity. So all supernovae start, and they are detected, hopefully, as they're going up and getting brighter. And this would normally be called phase 0 here. But we try to capture them before they reach their maximum brightness, and we do that by just finding out from some other supernova discovery method, and then we monitor it every few days, and we measure this light curve for a bunch of supernovae. So we track these, and these shapes of these curves tell astronomers what kind of supernova they are, how intrinsically bright they are. Then you can use that as a distance indicator. So this time axis along here is days, and this could be months. This could be like 3 or 4 months. So we're going to monitor this light curve of every discovered supernovae for a few months. We also take spectra. So this is a spectra. This is blue, 4,000, out to red, 9,000 or 10,000, much redder than our eyes see, of course. And we actually take spectra of all of these supernovae. And we do that with a spectrograph, an automatic spectrograph that's on our 2-meter telescopes. So the point is that you need, once they've been discovered, you need moderate aperture telescopes like ours, 2 meters, 1 meters, a scheduling strategy that allows access for months on end, that's our key thing, and substantial telescope time that we give by having lots of smaller telescopes, and we can do automatic spectroscopy too. Microlensing. The two things that we do mostly are supernovae, which are exploding stars, and microlensing. That's looking towards the center of our galaxy, the bulge, where there's hundreds of millions of stars. And they're all moving around. All the stars in the galaxy are going around. And so the line of sight against the background sources is changing very, very slowly. And every now and then, a star in the bulge will go around past a background object. And that background object will appear to get brighter. Sorry. So it will get brighter by a factor of 10 or so. And again, someone, MOA is one of these discovery things, Ogle is another, they find them, we don't find them, but they tell us, oh, there's something getting bright there, and we get on it as quickly as possible. Again, you're missing the time scale here, but this is like days now. It is actually tens of days, and we monitor it over that time, and if it's just a single star, we get a very smooth curve. And that's interesting, but it doesn't tell us much about what's around the star. If, however, there's a planetary system around the star, then that lensing effect might cut through the planetary system, and you can get a blip. And that blip, the strength and the duration of that blip, tells you the ratio of the mass of the planet to the star, and also the ratio of its distance, the planet, the size, the planet to the star. So these are very rare events, but when you're looking at hundreds of millions, you get many of these. The nice thing about microlensing is that it's sensitive to Earth-sized planets. Nothing else is. When we look at planets going in front of the star, we're obviously more susceptible to big planets like Jupiter-type planets. If we're looking at the reflex velocity, the star is oscillating backwards and forwards because there's a thing going around. That's all down to big planets. But these things can see down to Earth-sized planets. So most of our Earth-sized detections have come through this strategy. And again, based on the anniversary thing, I'll just mention that the Macho project was started about 20 years ago at Stromlo on the old Great Melbourne 50-inch telescope, which was, that was a favorite of mine way back when. That was destroyed in the fire. But this is basically a 20-year anniversary. And it's been done by many people since then, including telescopes here and by us. So this is the kind of stuff we do. We also do near-Earth object tracking. This is an example of a particular asteroid. It's 2010 AL something. I'm sorry it's not buried there. It's the one that came recently quite close a few years ago. This is it. Multiple exposures moving across the field. Right, so that's the track of the asteroid. This came within the moon's orbit. So it didn't come really, really close to the Earth, but it came within the moon's orbit. Right, so it's fairly close. And of course, this stuff has collided with the moon and with the Earth in the past, and it can do again. So this is all good stuff. And again, this was not found by us, but it was tracked by us. So let's go on. So I'm going to tell you more about the hardware and the way we operate the system. So we obviously want our sites distributed to allow continuous coverage. So they're spaced around the Earth at roughly 8 hours as the Earth rotates, intervals. And we have multiple telescopes at each site. So we could look, all the telescopes could look at the same source, maybe in different filters, but normally they're looking at different sources so we can multiplex what we're doing. And each telescope has more or less identical instrumentation so that the data can be combined. The astronomer who requests those observations does not know in advance which telescope will take his observations. That's all down to our scheduler. And so we have control software that operates things autonomously. Everything works autonomously. And this is our key thing. This is the one thing that we have that's different from anybody else. We have a scheduler that schedules requests from 100 people from 12 different organizations across 11 telescopes simultaneously. Everyone has a queue or a schedule for one telescope or maybe 2 telescopes. We do it for all of our telescopes all the time. And if the weather changes or one telescope goes out of action for some reason, the schedule just recalculates it and does it as best as it can. And we have, so this was actually the concept from Wayne Rosing 10 years ago, or he obviously had it in his mind, and that's what we've been designing and building ever since. Here is our 1-meter telescopes. These are all designed and built in-house. And if you know about telescopes, you will realize that these are not alt-az telescopes. I know that that's common nowadays, but you also know that the telescope up here is an equatorial telescope. It happens to have a C-ring, a big C-ring, and the telescope is inside the C-ring. So we actually took some of that design philosophy and built that into our smaller 1-meter telescopes. Now the reason we use 1 meters instead of 2 meters is they're cheaper, obviously. And they typically go as the diameter squared or even cubed. So they're much cheaper, a factor of 10 cheaper than a 2-meter telescope. We don't need a lot of light gathering power for our purposes. So we built these, designed and built these. We copied this system from some telescopes, including the AAT upstairs. We design them and build them. We have multiple copies of this, and we then test them. We build all of this hardware that actually controls the telescope. We build the carbon fiber tube we buy, but we build all the focusing mechanism. We're using Hextech mirrors in there. This is where the mirror cover goes. It's actually a Hartmann screen at the moment. And then we put them up on this test pillar inside our workshop, and we operate them for about a week and make sure that everything is working. And here's another one that's been assembled and is getting ready to go to a site. And then this is all in Santa Barbara, California. And and then we strip off the optics and we ship them in a container and we crane them through the open shutter. This has all been built, right? This has taken us some time to build. But we crane them in there, we put them onto the existing piers, we cable them up to the existing electronics, and it takes us about a week to be on sky and working. And we do that, that's obviously the power of, a production line. Here's our site in Chile. So here you can see 3 enclosures, 3 concrete pads, there's a pier underneath, 3 telescopes were installed there, and then there's a little container there that contains all the computers for operating this site. All the computers are inside that container. And they open and close, and they follow the instructions from this, and this receives instructions from Santa Barbara. This is our Australia site, and that's just over, which way? I think that way. And this is the UK Schmidt, which is now run by the Anglo-Australian Telescope. This is our 2-meter enclosure that's about 10 years old. These are our 2 1-meter enclosures, which are here at this site, Siding Springs, and this is the door. And in our case, it's easy to know which way you're going because the doors always point towards the pole. So this is pointing towards the South Pole here and the North Pole in the Northern Hemisphere. Here's some pictures of our 2-meter telescopes. They were already in place more than 10 years ago. The one here had to be significantly refurbished in 2005, but it's operating well now. And this is a zoomed out picture of that same site I showed you before, the Cerro Tololo, Chile site, the same 3 telescopes, the same container that runs it, a couple of cars in the foreground. This is a larger container that we use for storage. This is the 2-mast telescope here that was already on the site. This is the KMT telescope, which had no telescope in at the time this picture was taken, but that has been installed now, just as the crane that you can see over on the KMT telescope here is being installed. And what I'm actually pointing out to you here is we have a little enclosure here, and this contains 2 40-centimeter telescopes. And this is what we're actually expanding our network with right now, because, again, many of our sources are bright enough to be done with smaller apertures. We're also using these for educational purposes, so schools can get time on these telescopes. And this is the platforms that you will see over in the 2-meter enclosure over at the Faulkes Telescope. And that's where 2 more of these telescopes are going. And let me show you, here's an example of a 40-centimeter, again, the C-ring design. It's actually a Meade tube, there's a commercial optics, but we've replaced everything inside of it. Not the mirrors, but we've replaced the focus mechanism, the drive mechanism. None of the hardware was good enough, so we replaced all of that. And we're building these up, and we're actually deploying them. These are obviously, again, significantly cheaper than the 1 meters. So we can build a few of these and put them out there, and they don't cost us very much more to operate, and they don't take up very much space. And I think I'm getting actually fairly close to my end. I'll just show you pictures. This is our instrumentation on the 1 meter. We have a 3-wheel optical filter, so these go from ultraviolet through to far red, CCD technology. And this is what's called a Sinistro CCD. It's a 4K Fairchild CCD designed and built in-house. And these have a half a degree field of view, roughly the size of the moon on the sky. And this is what we use to monitor the sky. And we have all of these filters here. And one of these will be on each of our, we're just deploying them now, but they will be on each of our 1 meter telescopes. And they take pictures like this. Here's another, just a pretty picture of the sombrero. And we also have a spectrograph. And this spectrograph is on the 2 meter telescope. And it's, you can see it's a space frame design. It's very compact because it has to fit to the side of the 2 meter. And it's robotic. It has a low resolution, but it covers the full optical range from the ultraviolet out to the red limit of the CCD. It has a 30 arc-second slit that I'll show you, and it has, it has fully automatic acquisition and guiding, and we have one on each of our 2 meter telescopes. So here's what happens. Someone says there's a supernova, and it has these coordinates there. So we point our telescope, and we miss by a bit. and we then do a pattern match of that against all the catalogue stars, and we say, okay, it must be that object there, and we want that on the 30 arcsecond long slit. So the telescope does a little move, and then the starlight is going down the slit, and then we take a spectrum, and that might be 1,000 or several thousand seconds long, and we get the red light from green out to the far red, and from ultraviolet out to green, and so we get a spectrum, and we straighten that out, and we extract it, and then we get a low resolution supernova spectrum, similar to the ones I showed you early on. Yes, thank you. I'm almost finished. What is already in place? We have 2 2-meter telescopes, 9 1-meter telescopes. We want to deploy up to 5 more 1-meter telescopes. We are looking for extra funding because Wayne's put a lot of money into this, but he'd like to get somebody else to put some more funding in. We use the same software everywhere. We have a single network scheduler, and our data actually ends up in the IPAC archive. That's at Caltech, and that's where people get their data from. And we're working on a set of high-resolution spectrographs, one of these bench spectrographs at each site, including one here, fiber connected to each of the 1-meter telescopes, and we use the same method. We put a star onto this fiber, and we measure the velocity to a few meters per second, and that enables us to look at these exoplanets and see how fast the star is bouncing backwards and forwards. And that tells us whether it's a planet or if it's a double star. Okay, so, and we're also deploying these 40-centimeter telescopes. And this is my final slide. This is a picture of us. It's a couple of years old. This figure in the front is Wayne Rosing. So I've been happy to spend a lot of his money, so is of everybody else there. But these are our engineers, our technical staff, our programmers. This is Las Cumbres Observatory. And we are operating these telescopes along with other people in different parts of the world, including in Australia.